This screencast is going to focus on free energy, specifically Gibbs free energy. And Gibbs free energy is kind of the final say on whether a reaction will be spontaneous. So we talked about the fact that, if we want to look at just enthalpy, exothermic reactions tend to be spontaneous, right? And endothermic reactions tend to be non-spontaneous. These are just kind of guidelines, right? So if you had a negative delta H, those would be spontaneous. If you had a positive delta H, those tend to be non-spontaneous. And then we introduced this idea of entropy, or delta S, and we said that if something has a positive delta S, that means disorder is increasing, and those tend to be spontaneous. If we have a negative delta S, that means disorder is decreasing, and those tend to be non-spontaneous. So when we're looking at these independently, we can get an idea of whether a reaction will be spontaneous. But we also said we've got to look at temperature. And so temperature is definitely something that will impact whether or not a reaction will be spontaneous. So the final say on whether a reaction will be spontaneous is Gibbs free energy. A little typo right there, energy. All right, so if Gibbs free energy is negative, then that means the reaction will be spontaneous as written at that particular temperature. If you have a positive delta G, that means it will be non-spontaneous as written at that specific temperature. So just be careful, when you're answering questions, especially on the AP exam, if they ask you to predict spontaneity, then you've got to go to delta G. Now, if they ask you to look at entropy independently or enthalpy independently and say, hey, will this reaction tend to be spontaneous or not, then it's fine to use the exo-endo or the increasing disorder, decreasing disorder explanation. But if they want like a hard and fast, will this be spontaneous, then you've got to go to delta G. All right. This little note right here, it says, during a phase change, delta G is 0. That's considered like an equilibrium position. And so at that point, if delta G goes to 0, then you end up with 0 equals delta H minus T delta S. And so they've just rearranged this, right? Notice that this is very similar to what you guys saw. Sorry, I'm solving this in my head. Delta S is equal to delta H over T. This is very similar to the formula we saw in the previous screencast, but the negative's not there. And the reason the negative's not there is what we were doing before was delta S surroundings. We said it was difficult to solve for delta S surroundings, so we put it in terms of the system. Well, this is obviously talking about the system, and so that's why you won't see that negative there, just to clear that up. All right, and again, it will only be spontaneous if delta G is negative. And just a little tip to watch, we talked about enthalpy is usually given in kilojoules, and delta S is usually given in joules. So you want to make sure that those jive and get them both into kilojoules. All right, so practice 6, basically just plugging into a formula. They want you to figure out if it'll be spontaneous or non-spontaneous. And so we need to solve for delta G. So delta G equals delta H minus T delta S. All right, so we've got 40 minus, I'm going to change this to kilojoules, so divide it by 1,000. So I get 0.3 times 130. So delta G for that one comes out to be 1 kilojoule. So this is a positive delta G, so this would be non-spontaneous. For B, we plug in and solve. We get 40 minus, this time entropy is negative, so we have negative 0.3 times 150. And for that one, it comes out to 85 kilojoules. Again, still positive, non-spontaneous. Now, just a side note, you can actually look at the values of delta G and see relative to each other how far away these are from being spontaneous. So hopefully it makes sense that this is a positive 85, this is just a positive 1, this one is actually closer to being spontaneous than this one is, right? Because if you think of 0 as kind of the crossover line where we go negative, the closer you are to 0, the more likely, or the closer you are to becoming spontaneous. And we'll talk about what we can do with temperature for some of these systems to make things spontaneous. All right, in the last practice, we've got negative 40 minus 0.3 times 150. For this one, we get negative 85 kilojoules. So finally, a negative delta G, so this one would be spontaneous. And if you think about why, right, we've got an enthalpy value that's negative, so that's going for it, it's exo. We have a positive delta S value, so that means you are increasing disorder. So when you have that combo, an exothermic reaction, disorder is increasing as long as that temperature is good, right? You're going to have a spontaneous reaction. Okay. So this next part of the notes is something hopefully that will help you kind of rationalize in what cases can you say, oh, that system will always be spontaneous or will, not be spontaneous. So there's 4 different scenarios. So if I think about my Gibbs free energy formula, right? Temperature is always going to be a positive number because it's Kelvin, and the Kelvin scale is all positive numbers, right? So if I want to look at spontaneity, I know that I want delta G to be less than 0 to be spontaneous. So the first case we're going to look at, if we have a positive delta H and a positive delta S. So these two terms are kind of in conflict with each other because a positive delta H means that it's endothermic, right? And those tend to be non-spontaneous. But this entropy term, positive delta S, that means disorder is increasing. That's actually going for spontaneity, right? So if you think about delta G, in endothermic, you're going to have a positive number here. In the formula, you have that minus that's always there. We know temperature is always going to be positive. And then we have times a positive number. So sometimes this can actually be a spontaneous reaction, and sometimes it'll be non-spontaneous. Because what will happen if we want it to be spontaneous, right? We're going to subtract off this term. So this term, once it overcomes this term, then we can get a negative number. So will that tend to happen at high temperatures or low temperatures? Well, if we want this term to overtake, and so this is just a positive number, this has to be positive, right? Then we want high temps to be spontaneous. And we're not using any numbers here because College Board loves doing this. They love giving you a scenario and saying, well, will this always be spontaneous? Will it always be non-spontaneous? Or under what conditions will it be spontaneous? Okay, so that's why we're kind of going through these without numbers. So this is a either or case, and it's temperature dependent. All right, case number 2, still positive delta H, so that means endothermic. So that means not going for spontaneity on the enthalpy term. Negative delta S, well, that means disorder is decreasing. So that's also going against spontaneity. So if you think about your delta G, you have a positive number minus, you've got temperature times a negative number, right? So when you multiply these guys together, and then you do minus and negative, then no matter what, it turns into plus a positive. So if this is positive, and this is plus a positive, then no matter what, delta G has to be greater than 0 or a positive number. So that means this will be non-spontaneous for all temps. Okay, you got both terms going against spontaneity, and that would be the math as to why. All right, case 3, we've got negative delta H, so that's favoring spontaneity because it's exothermic. We have positive delta S, that means an increase in disorder. That is favoring spontaneity. And so what do you guys think? If both are favoring spontaneity, when we go and we look at the math, you've got a negative number minus temperature times a positive number. So you have a negative, and you're subtracting off no matter what a positive number. So if this negative you're subtracting off a number, it's just going to get more and more and more negative. So no matter what, delta G will be less than 0. So this will be spontaneous for all temps. Spontaneous for all temps. So these two are nice because they're, what do I want to call it? Straightforward in the sense that there's no wiggle room. There's no temperature dependence, right? This case, both against, will be non-spontaneous. This case, where both are for, will be spontaneous. So case 1 and case 4 are the only ones where you have to think about temperature, and I'll show you how to solve for it in just a minute. So for this last case, we've got exo, that's favoring spontaneity, but here we have a decrease in disorder, and that is not favoring spontaneity. So when I go and do my delta G, I have a negative minus temperature, which has got to be a positive number because it's Kelvin, times a negative, right? And so minus a negative can become plus a positive. So when this term takes over this, right, it will become non-spontaneous. So in order to be spontaneous, in order to be a negative number, we would want temperature to be small. So if temperature is small enough, then it will be spontaneous. So you could say spontaneous for low temps. And like I said, I know we're not using numbers here, so you're like, well, what temperature? We'll actually solve for it using an inequality so that you can see. Alright, so for practice 7, Br liquid going to Br gas, right? This is an endothermic process because we're having to overcome intermolecular forces in order to turn it into a gas, and so you'll see that our enthalpy value is positive. In terms of disorder, we also have a positive because you're going from a more ordered state to a less ordered state. So they want to know at what temperatures will it be spontaneous. Alright, so if we have delta G is equal to delta H minus T delta S, if we want it to be spontaneous, we want delta G to be less than 0. So we can take this and substitute in. So we want delta H minus T delta S to be less than 0. So you will actually use inequalities that you learned in either Algebra 2 or Pre-Cal. Alright, so we plug in, we've got 31 kilojoules minus, we don't know temperature, but we know our delta S is a positive 93. So we've got 0.093 is less than 0. So we'll bring this guy to the other side, so negative 0.093 T is less than negative 31.0. To solve the inequality, we divide both sides by negative 0.093. And if you remember, when you are dividing by a negative or multiplying by a negative, you've got to flip the direction of the inequality. So the temperature would have to be greater than 333 Kelvin. So that's how you solve for temperature. Alright, and number 8, a similar scenario, but they're actually giving you some, real-time data. They're saying the boiling point of water is 373 Kelvin, or 100 degrees Celsius, and they want to know how this compares to the minimum temperature in order for this to be thermodynamically spontaneous. So again, delta H is positive, entropy value is positive. They want to know where would this happen, spontaneously. So the same thing, delta G is equal to delta H minus T delta S. We want it to be, we want delta G to be less than 0, so that means we want delta H minus T delta S to be less than 0. So rather than plugging in this temperature, right, we're solving for the temperature, just like we did here, and then we're going to compare it. And you'll see why the boiling point of water is 100, and why that happens spontaneously as soon as it gets to 100 degrees Celsius. So we've got 44 minus temperature times 0.119 is less than 0. So negative 0.119 T is less than negative 44. Divide both sides and flip our inequality. So the temperature comes out to greater than 370 Kelvin, which if you compare to the boiling point is pretty close. And so that's why water boils spontaneously when it gets to 100 degrees Celsius.